Howdy students, this is going to be Nuclear Chemistry Part 2. In this video, we're going to talk about transmutation. We're going to look at half-life. We're going to look at a decay series, and then we're going to finish by talking about carbon-14 dating. So let's get to it. Nuclear transformation, also called transmutation, is changing one element into another. So we can bombard different elements with alpha particles. Here's an example of that, nitrogen-14. When we add a helium atom to it, we form oxygen because we have added those neutrons, and we get oxygen-17, which is an isotope of oxygen and a proton of hydrogen. So we've actually turned nitrogen into an atom of oxygen. Now we can also bombard with neutrons, which is where we will alter the mass numbers and form a different isotope of uranium here in this example, 238 to 239. So nuclear transformation, again called transmutation, is how we get different elements on the periodic table. So a long time ago, before we had particle accelerators and cyclotrons, the periodic table was fairly limited. But now that we've actually been able to alter the DNA of an atom, we can actually expand the periodic table. And in 2018, the periodic table was actually completed. We finished and got all the way up to element 118 over here. Half-life, by definition, is the time required for one half of a radioisotope to emit radiation and decay to products. So it's the time that it takes to start with one whole and end up with a half. The longer the half-life, the more stable the isotope. The longer it stays intact, the more stable it is. Half-life varies from fractions of a second to millions of years. The smaller the half-life, the quicker an element will decay. So here's an image. We have, at the very beginning, we have a newly formed mineral, and you'll see that all of the atoms here are black, 20 black and 0 red. And after our first half-life, and we don't know how much time that takes here on this graph, but you'll see that the fraction goes now to 10 and 10. We have decayed half of our particles. And then after that, another half-life, half of the 10 goes to 5. And then 2.5, and we could keep halving and actually never reach 0. And so this is an exponential curve here. So here's an image showing the different radioactive decays, starting with uranium-238. We call this a decay series. And the half-life is 4.47 billion years, which seems absolutely crazy. But over time, we go through alpha radiation, and we turn into thorium-234. Now, the half-life is only 24 days, so this one doesn't last very long. And we could continue down and look. Some of these, look at polonium-214, very unstable. Half-life is just a fraction of a second. And then eventually you get to a product that is stable and will actually never decay, like lead-206. So if nitrogen-13 decays to carbon-13 with a half-life of 10 minutes, how long is 4 half-lives? Well, if each half-life is 10 minutes, we're just going to multiply those two numbers together in order to figure out the time. So that would be a total of 40 minutes. And if we started out with some amount, say 10 grams, what we could do is go through 4 half-lives and actually figure out how much we have left. So if we start with 2 grams, how many grams will remain after 4 half-lives? Well, we know that it took 40 minutes to do this, but how much will be left over? So after 1 half-life, we'll be at 1 gram. We half it, right, divided by 2. After a second half-life, we'll be at 0.5. And if we go through another half-life, we'll be at 0.250. Now that's 1 half-life, 2 half-life, 3 half-lives. So yeah, we have 4 numbers, but we haven't gone through 4 half-lives yet. So we got to go through one more, divide by 2, and our final answer would be 0.125 grams. So after 40 minutes, we have 0.125 grams left over. Phosphorus-32 has a half-life of 14.3 years. How many grams remain after 57.2 years from a 4-gram sample? So this one's a little more complex. We start with 57.2 years, and if I divide by the amount of time in a half-life, it will tell me, after years cancel, the time of the half-life. And in this case, we're going to go through 4 half-lives. So if I multiply 14.3 by 4, I'm going to get 57.2 years. So if I'm starting with 4 grams, I'm going to go through 4 half-lives. 1, 2, 3, 4, and I'm dividing by 2 every time. And I'm going to end up with 0.25 grams left over. So again, total time divided by the time of the half-life, and that will tell you the number of half-lives that you go through. A decay series is a series of decays that eventually leads to a stable product. We showed you a picture of this a couple slides ago. The heaviest nuclide of each decay series is called the parent nuclide. The nuclides produced by its decay series are called daughter nuclides. Uranium-238 generally is the top of the decay series, not always, but it shows the eventual decay into lead, specifically lead-206. So here's an example. Here's uranium-238. We call that the parent. Everything else is called a daughter nuclide. And the key says that if I'm going down and to the left, I'm going through alpha radiation, which again is a helium atom. And then if I'm going back to the right, I'm going through beta radiation. And so if we follow the path, we can continue all the way down, and eventually we end up at this final resting product. And you'll notice there are actually multiple routes here. You'll see multiple lines together. We can reach lead-206, which is stable, by taking different paths. Here's another example of a decay series. Looks a little bit different. Otherwise, everything's the same. The key is just a little bit different. Beta goes up and to the left. Alpha still down and to the left. But eventually, our stable product is the one that's down here. Last thing we'll talk about in this video will be carbon-14 dating. So how does carbon dating work? Carbon-14 is an isotope of carbon. We have carbon-12. There's also carbon-13, and there are others. Carbon-14, though, is produced in the atmosphere when higher energy neutrons from space collide with a nitrogen-14 in the air. Carbon-14 combines with oxygen to form CO2, so that carbon-14 atom that combined with a nitrogen actually finds its way into different organic matter, and then we can actually trace that carbon-14, and there's ways to trace and figure out how much carbon-14 is in an organism. And so they actually use this process to date fossils and different artifacts, anything that contains carbon. But if it doesn't contain carbon, then we have no process for dating that. So the proportion of carbon in the atmosphere is constant. Carbon-14 to carbon-12 ratio is used to identify the age of wood. We call it petrified wood and other organic artifacts. So this is important. I would have you underline this or circle this, but the half-life of carbon-14 is 5,730 years. So the time it takes to go through a half-life is a long time. And again, we can only use it for organic materials, which are things that contain carbon. If it doesn't contain carbon, then we can't use this. Now, this value is adjusted for change depending on the percentages of carbon-14 in the atmosphere and in the ground over different years. Here is the decay process for showing the radiation into a nitrogen-14 atom. You'll see that we have a -1 particle here, which is how we came from nitrogen-14 in the atmosphere into carbon-14 into the ground. So carbon-14 was made famous with a guy that they called Iceman. They dug him out of the ground, and they used carbon-14 in order to figure out how old he was. And because they knew the time of the half-life, they estimated that he was about 5,700 years old. Now, there's another story to him, and they were actually able to identify, because he was preserved in the ice so well, exactly what happened to him. And apparently, he was betrayed by his own people. Interesting story. So if we're using carbon-14's half-life, which is 5,730 years, if the C14 in a sample is a quarter of what it was in living organisms, how old is the object? So to have a quarter remaining, that means that 2 half-lives have passed. Let me show that up here. If we start with a whole, after our first half-life, we would have a half, and then after our second, we would have a quarter. Because we went through 1 half-life and 2 half-lives, and we know the time of each half-life, we can figure out roughly that whatever this artifact was, whatever this organism was roughly 11,000 years old.